Hello Mautas! We can finally answer that big question. What are gravitational waves? But many more. How they were predicted, what they consist of, and how they are detected. We will answer all of this today. It is a wonderful day, a unique day, a special day, a historic day for us, because we will finally understand it in all its magnitude. So without delay, we now enter this chapter where we will finally understand, learn everything about gravitational waves. And so we enter Miguel's office with great curiosity. Finally, because we want to continue the story, we want to know what has happened. We have already seen the mathematical foundations of Einstein's theory of gravity, a theory that puts us on the trail of gravitational waves. And now it's time for the next step, the obvious one, to learn a bit more about this prediction of general relativity, the prediction of gravitational waves. Look at the beautiful way Miguel tells us about it.
Einstein's general relativity predicts a series of very interesting things. Let's say its first great success was precisely the one I just mentioned. It explained the precession in Mercury's orbit. That was the first important application, but it is an observation that was already known.
The next prediction was the prediction of the deflection of light by the sun due to the equivalence principle.
And that is verified very soon in 1921 by Eddington, which is also what I mentioned. He conducts a study during a solar eclipse, observing the position of stars near the sun, and sees that the light was deflected. Exactly what Einstein's theory said. In fact, that is what makes Einstein very famous quickly, because it appears in the newspapers. Physicist predicts that light is deflected by the sun, and so on. He becomes very famous. But there are other very, very important predictions that have been confirmed over the decades in the last century. For example, the theory predicts the existence of black holes, which for a long time were thought to be speculative and that we now know existed. But it also predicts something that Einstein predicted immediately. That is, since 1916, he had already predicted it. And in fact, he was not the first. No, it had already been mentioned many years before that. Well, if gravity propagated at a finite speed instead of infinite, according to special relativity, not even general relativity, then if gravity had to propagate at a finite speed, there would have to be wave phenomena. Because if something propagates at a finite speed, waves of something arise. So the idea of these gravitational waves had already been mentioned for a long time, but Einstein, already equipped with this final theory in 1915, 1916s, in fact, he makes a calculation and predicts that there must be these things that should be called gravitational waves, which should be produced when we have systems where gravity is changing over time. This should predict disturbances in gravity moving outward at the speed, precisely at the speed of light. In fact, we call it the speed of light because it was the first thing we discovered that traveled at that speed. But gravity travels at the same speed. We could have called it the speed of gravity because it is the same speed. So Einstein discovered that his theory predicted these gravitational waves. The idea of gravitational waves took a long time to be fully accepted. As I was saying, the theory is very complicated. The equations are very complicated. And there are a series of effects related to how one chooses the coordinates, how one chooses how time progresses, because time is relative. So I have to choose which time I select. Space is curved, I have to choose coordinates, how I describe this curved space. And a series of problems with choosing coordinates, choosing time, sometimes makes it very difficult to interpret the solutions of the theory. For a long time, this was not well understood. In fact, Einstein, I quote, when he makes his first calculation, says, there must be gravitational waves. And these gravitational waves are of about 5 types, or what we would call 5 polarizations. That is, in electromagnetic waves, there are 2 polarizations. The electric field can oscillate like this, and the magnetic like this, or they can do it like this. There are 2 polarizations rotated 90 degrees. That's what we do when we wear polarized lenses, which prevent one of the polarizations from passing through. So we see fewer reflections. Einstein said these gravitational waves must have 5 polarizations. And then, shortly after, Eddington, who is the person that conducted the famous experiment, well, not experiment, the observation of the solar eclipse where the deflection of light by the sun was detected, was one of the people who best understood relativity at that time. At that time, there were very few. Relativity was very new. Very few people understood the theory. Eddington took Einstein's calculations, did some calculations, and realized that out of the 5 polarizations Einstein mentioned, by just changing certain choices in the equations, 3 choices of how he measured things, etc., 3 of those 5 propagated at any speed he wanted, not at the speed of light, but at a speed he invented. Very strange, right? Then he declared at some point that Einstein's gravitational waves propagate at the speed of thought, which was a mockery. He was saying, now these gravitational waves of Einstein do not exist. They are a mathematical artifact of the theory and are not physical. They have no physical manifestation. And it remained like that, as if gravitational waves might not actually exist for decades. Even in 1936, Einstein himself, who is a collaborator, Nathan Rosen, who was his collaborator on many articles at that time, tried to publish an article in which they claimed to demonstrate that gravitational waves actually did not exist, that they were indeed a mathematical artifact and everything was a problem and did not exist. And I say they tried because they couldn't publish it, because they sent the article to Physical Review, which is one of the most important journals in physics. No. Now, Physical Review sent the article for review. This is a usual system in physics where you send an article to a journal and they send it to be reviewed by referees who are other experts in the field, who read it, remain anonymous, but read it and tell you that the article is good or it's bad, right? A referee pressed the read it and replied to the journal, this article has several errors. So the conclusion is, Ian is wrong, they have to correct the errors, because the response reached Einstein. Einstein was furious because at that time, journals still didn't have the habit of always sending their articles for review. Sometimes they didn't send them for review and sometimes they did. And Einstein had never experienced that before. So the first time they send one of his articles for reviews, they tell him the article is wrong and that the journal rejects it. Now Einstein becomes furious, he decides never to publish in the Physical Review again, a decision he keeps. And as that article is not published, months later, a colleague approaches Einstein and says, hey, I already saw your article. Yes, maybe the referee is right. Why don't you take a look at it? So Einstein reviews it and realizes that indeed there are errors. He corrects them and realizes that now it no longer proves what he believed, that it no longer proves that gravitational waves do not exist, but rather finds a different expression for gravitational waves and finally publishes it in a rather unknown journal, but no longer proving that gravitational waves do not exist. But it's an interesting anecdote because in 1936, even Einstein himself almost thought that gravitational waves did not exist. No? The situation remained like this for another 20 years. No? 1956, 57, I don't remember the exact year, there was a very famous conference he held. It is the first International Congress of General Relativity. Today we call it GR1. It was a congress held in the United States in Chapel Hill, where all the experts in relativity in the world gathered. At that time, there weren't many. They all fit in one room, and they invited Feynman. Feynman, who is very famous Nobel Prize winner, very famous for other things, for the elementary particles quantum electrodynamics. They invited him, and he was very good at physical intuition as well. So he goes to the Congress and shows them a physical argument where he basically does a calculation showing that a gravitational wave, one of those Einstein talked about, is imagined to have like a wire, a metal wire with a bead threaded on the wire. It shows that if the gravitational wave passes, the bead will move relative to the wire and there will be friction, and that friction will produce heat. So he says, let's see, if gravitational waves are a mathematical artifact, heat should not be produced, heat is energy. So that shows he mathematically demonstrated that gravitational waves produced energy in a mechanical system, so they had to be real. So that is like the first argument, and it comes from Feynman, that gravitational waves are not a mathematical artifact, they must be real. But notice that this is still a completely theoretical term. They were purely theoretical arguments based on solving complicated equations. There was no observation that gravitational waves were real, but at least from there, theoretical physicists were convinced. Well, these things surely are real, and if they are real, then they should be produced out there in the universe, and we should be able to detect them.
What happens is that they are very weak. Gravity is the weakest force of all. And that might be hard for people to imagine because it's the force that keeps us on the ground right now, and that would kill me if I fell from 3 floors. Gravity, right? But that's because we have a huge planet beneath us, right? The gravity between 2 particles is practically negligible. Gravity is the weakest of the forces we know in nature. And that means gravitational waves, in turn, are very weak. And they are so weak that they are very difficult to detect. They pass through here as if nothing. We don't feel them. No device feels them. They are very difficult to detect. And most scientists at that time, still in the 1960s of the last century, thought that detecting gravitational waves would be impossible even if they did exist, that they were simply so weak that no, the technology to detect them did not exist. And that started to change since in the 60s, a physicist named Joseph Weber, who has already passed away, I think he died in the year 2000, he said, no, surely they can be detected. How could I detect them? And he said, well, I am going to build a device and I am going to use a phenomenon called resonance. A resonance is a well-known physical phenomenon where if you have a system that likes to oscillate at a certain frequency and you hit it precisely at that frequency, it starts to oscillate more and more strongly and the oscillations amplify.
He said, Thomas Sharp, so I am going to build an object that has oscillation frequencies similar to those I would expect to come from space in gravitational waves, which turns out that if one does some calculations of binary system, stars, etc., one concludes that they should emit gravitational waves of the order of a few kilohertz, 1,000 cycles per second, more or less. I am going to build an object that has natural oscillation frequencies around there, and I am going to put it here and wait to see if it oscillates, and I will put some very sensitive detectors to see if it oscillates. The object turned out to be an aluminum bar weighing about 3 tons, cylindrical. He built 2. Why did he build 2? Because what I want is to see if this aluminum bar oscillates, and the oscillations are going to be very small. The problem is that this bar oscillates if a bus passes by the corner. This bar oscillates if I walk around it. This bar oscillates if I sneeze. It is very sensitive, and the oscillations I am trying to detect are smaller than that. So what do? I build 2 bars, place them very far from each other, 1,000 kilometers apart, and I wait for them to oscillate a little, but exactly at the same time. That is what we call incoincidence. So if that happens, if both oscillate exactly the same at exactly the same time, I know it wasn't someone passing by or someone sneezing, but something that affected the whole planet and therefore must come from space. So he built these bars, and around 1968 announced at a scientific congress that he was detecting gravitational waves coming from the center of our galaxy. This caused a stir. On one hand, people got very excited. Gravitational waves exist. On the other hand, doubts quickly arose. A theorist said, that it's not possible for you to detect gravitational waves with this device. Simply put, the calculations don't add up. That is, your device doesn't have the sensitivity to detect gravitational waves coming from the center of the galaxy, unless suns were exploding in the center of the galaxy every day. And that doesn't happen. So this doesn't make sense. The experimental group said, well, if he detects them, why don't the others? So they built identical bars, even better ones, even cryogenically cooled to extremely low temperatures, so they would hardly oscillate unless something happened and no one saw anything. No experimental group could detect gravitational waves besides Weber. The theoretical calculations didn't add up. And then, after a few years, people became convinced that who knows what Weber was doing wrong, but he wasn't detecting gravitational waves because no one else could see them. Weber himself was never convinced, which was a bit sad. Even in the 90s, he would go to scientific conferences to talk about his latest detections of gravitational waves, and practically no one would attend the talks because no one believed him. And yes, the consensus today is that he was doing something wrong. He never detected them. But he did leave the idea that maybe the idea of detecting them wasn't so bad, and that it needed to be done with more work, but using a better method. And in the 1980s, they came up with a different method. Instead of using these resonant aluminum bars, they thought of using an interferometer. An interferometer, it does not send a laser beam. It splits it into 2 paths at a half mirror. Then they bounce back on mirrors that are very far away, return, recombine. And since light is a wave, if the paths are identical, there is constructive interference, and I have a lot of light in the detector. If the paths are slightly different, there is interference, and I have less light in the detector. And this is interesting because if I have my mirrors at the ends hanging from cables free to move, and a gravitational wave passes and moves them, it turns out that it moves them precisely if they are at 90 degrees, bringing one closer and moving the other away at the same time. It is a property of the gravitational wave. So a gravitational wave would move one mirror away, bring the other closer, and I would see a change in the interference pattern. So that should work very well. But when you do these calculations, you realize once again, gravity is so weak that for the effect to be noticeable, I have to have gigantic interferometers. I have to have these mirrors several kilometers apart so that I can notice the effect. The bigger, the better. So they decided that they had to build interferometers, but they had to be several kilometers long. First, they built some prototypes. They built a prototype in Scotland and another in California, which were 10 meters long, and another was 30 meters long. They didn't see anything, but, well, they were figuring out how to handle these things. Finally, in the early 90s, 3 people presented a project to the National Science Foundation in the United States, requesting several $100 million to build gigantic gravitational wave detectors. They were Barry Barish, Kip Thorne, and Ronald Draper. They presented this project, finally got the money, and started building these large gravitational wave detectors called the LIGO project, Laser Interferometer Gravitational Wave Observatory, which is the acronym in English. Finally, they built 2 of those detectors in the United States for the same reason as Weber. 2 and very far apart, because what you want is for them to be at the same time exactly. And later, the Europeans did not want to, fall behind. So years later, they started building a detector in Italy, the Virgo project.
And also, well, the Japanese didn't want to be left behind. So many years later, a Japanese detector started. But, well, the first ones were the Americans, the LIGO project. And after many years of construction, testing, etc., finally in 2015, September 2015, a gravitational wave signal was detected for the first time coming from the universe, which now everyone was convinced of. All possible tests were done to ensure there was no doubt, and it was the first detection. This led to a Nobel Prize in Physics, eventually 2 years later, to the people who initially created this project. And from 2015 to date, more than 100 gravitational wave events have already been detected. All of these apparently have been the collision of compact objects. When you have two very compact astrophysical objects and they collide, this is a brutal disturbance to gravity. In fact, the most brutal are when two black holes collide. If you have two black holes that collide, this produces a huge disturbance to gravity. And these are the ones we have detected. Apparently, there are a couple of examples where what collided were not black holes, but neutron stars. But those are smaller and therefore have to be closer for us to see them. But black holes are so large that they can be seen even from very far away. And, well, people might also ask, how do two black holes collide? And they just happen to meet by chance out there. No, they don't meet by chance out there. They will never meet. What happens is that they were born together. 2/3 of the stars in our galaxy, for example, or in any galaxy, live in pairs. They are binary systems where one star orbits the other. If these are very large stars, at the end of their life, they explode in supernovas, but a remnant remains, which is the black hole. So you end up with two black holes orbiting around each other. Also, due to the supernova explosion, there was a lot of friction, and that brings them closer. Also, they end up very close, orbiting each other very quickly, losing energy precisely by emitting gravitational waves. And after many millions of years, they collide. Now, this takes many millions of years for each pair of black holes, but the universe is very large. There are billions of galaxies. So this must be happening every day somewhere in the universe. And if your detector is good enough, it should be detecting these things at great distances. And that what is happening almost today. They are detecting one of these collisions at the rate of 2 or 3 times a month somewhere in the universe. So gravitational waves were finally confirmed. It is perhaps the confirmation that took the longest. Einstein predicted them in 1915-16, and we detected them in 2015, 100 years later, but there they are.
A truly unique and historic moment, a euphoria and a celebration to which another parallel milestone contributed. I would say it is at the same level of importance as the previous one, because without it, it would not be the same. Gravitational waves were also mastered in the virtual world, in computers, in simulations. It was a very important step to complete the physics of gravitational waves and make the most of this measurement of this experiment. And in this chapter of the history of science, Miguel was a prominent protagonist. But let's move on to the next chapter, because there we have a lot of time and space to learn it in all its dimensions. See you soon!